So I will give you a brief overview of on the topic of optimization within machine learning. Of course, I don't have that much time during the 3 lectures that I'm speaking on this topic to really go in depth about anything. So I'll cover it at a very somewhat superficial level, but hopefully you'll get a bit of the flavor of the kinds of optimization problems and some basic optimization techniques that every machine learning person should be aware of. I'll also mention while during my lecture some challenging toy problems. They are not research problems of interest to machine learning per se, but if you want to exercise your skills based on what I talk about, I encourage you to try your hand at those challenge problems. They're very interesting, at least to me. So I'm going to focus today on just in this first lecture on some basic building blocks to establish a vocabulary of the concepts that we are dealing with. And you will see maybe because this is like establishing a vocabulary, that means there's probably going to be tons of words, and you're not going to, most likely for those who are unfamiliar, don't push yourselves to try to absorb all the vocabulary. Hopefully you get the main ideas, and all the details that I'm speaking about, they are in my slides, so you can quickly refer back anytime, okay? Some of the useful material. So my webpage has a link on teaching which contains several links to related material in much greater detail. And for the second lecture, I'm going to talk after establishing the vocabulary right now. In the second lecture, I'm actually going to talk about algorithms that you should be aware of. And for that, really the book to go to is Yuri Nestor's book on Introductory Lectures on Convex Optimization. For the basics that I'm going to talk about right now, I will refer you to this excellent book by Boyd and Vandenberge on convex optimization. It's mostly, let's say, on convex analysis, and several other books. And in my last lecture tomorrow, I'm going to talk more about stuff that is closer to the research edge of what we're doing in machine learning right now, to give you a quick overview of things. And I have much more elaborate lecture slides on the material that I'm talking on from a course of mine, from 2 courses of mine. And there are sister courses which contain some overlap with what I'm talking about, Speaking Boyd's webpage. And of course, I don't need to tell you this, but many of these things, the kind of things that I talk here, they eventually used in a bunch of papers in the standard conferences or journals in our area, okay? So that's the backdrop. This is probably for the beginners in the area, this list of references is probably super important. Okay, so what I'm going to talk about today is give a gentle introduction, which I am trying to do now, then do somewhat less gentle introduction to the actual concepts of interest today. And then in the afternoon, I'm going to actually talk about algorithms, moving from standard algorithms to large-scale optimization, which is the kind of optimization that is really crucial to machine learning. And tomorrow I'll talk about more research edge directions on non-convex optimization, of which, of course, people know that deep learning type stuff is a special case. Okay, so that's it. So because now 1 week has essentially passed in this class, so I assume all of you have seen supervised machine learning. And just to remind you then, you have a bunch of data. It's only on this slide that I'm going to use X, the machine learning notation for training data X. After that, I will, maybe to the annoyance of some people, switch gears, and X will actually be the variable of optimization. And I'm just using that notation because any literature you read in the world of optimization is typically going to use X as the variable. But anyhow, we have training data, and the goal is to learn some kind of prediction function. Like you had linear predictions with some features that you manage to encode, or in neural networks you have a nonlinear prediction function, and estimating your prediction function to look at training data to come up with a good prediction function, estimating its parameters, you typically set it up as the goal of trying to minimize some loss. And I already used the word minimize, which is why estimation problems in machine learning are almost always cast as optimization problems. And within other areas of machine learning beyond just supervised learning, unsupervised learning, or other setups, formulations are kind of different, but ultimately optimization is at the heart of what we try to do. So there's some risks that we want to minimize, some likelihood we want to maximize, etc., etc. Okay, so that was the gentle introduction. Now we'll get to the actual stuff. So this is the one thing we're going to keep in mind at all times. That's what we are talking about. We are going to look at problems where we want to minimize the function f over some constraint set S. And everything I'm going to talk about is just going to be an instance of this. And you can imagine the variety of things you can do in terms of how you select an F or how you select an S. But the principles are going to be similar. And in particular, I'm going to divide my discussion into two parts. One is to look at setups where the function f looks nice. Others is where it looks maybe nicer but harder to work with. So I'm going to tell you some stuff about those types tomorrow. These are called convex functions. And you can kind of, from the picture, see why we may prefer one over the other. If you're trying to minimize, and this function seems to have seems to be slightly easier to minimize. And okay, that was a gentle introduction. So now let me establish some background and vocabulary necessary for talking about all the concepts that are coming up. But even this, I'm going to go through some things, and my slides contain more material than I'm going to speak. But that material is there for you to look back at later to reinforce what I'm saying. Okay, so I will mention, for instance, theorems, but sometimes I have included short proofs, but I'm not going to go through the proofs during the lecture for lack of time. But the proofs are there in case you attempt to prove it yourself and want a quick hint or something. Okay, so let's start with convex analysis. And that first nice looking function that I said, this is called a convex function. So let me describe to you the language of convex analysis. That's why studying such functions and how one operates on them, that's what we'll do in convex analysis. So here's the simple vocabulary. So we'll say a set is convex if for any 2 points in the set, if you draw a line segment between them, that line segment lies inside the set. Pictorially, that's really easy to look at. That particular property turns out to be fascinating and of great importance. I will show you, in fact, tomorrow another instance of that, just this simple property of the entire line lying inside your set, how it translates into other kinds of cool optimization. So as an analogy, if you see, we define convex sets as sets where these types of linear combinations with distinguished constraints on the coefficients, those points lie inside the set. And you can loosen those, or you could have tightened those depending on your perspective. If we remove the restrictions on the lambdas, you get linear combinations. If you remove this equality, then you get what is called a conic combination. If you keep the non-negativity, but you just drop this. And different restrictions on how you combine your objects lead to different kinds of algebra. So linear algebra, clearly everybody must have seen during their undergraduate. So that deals with this world. And because there are no constraints, linear algebra mostly becomes a story about solving linear equations. I'm oversimplifying. In the convex world, because you have constraints here on how you can combine stuff, the amount of algebra you can do with them is somewhat restricted, and it turns out that convexity becomes not a study of equations, but a one-sided thing, a study of inequalities. So that's just intuitive background behind how you may want to think about the convexity. And feel free to be creative. You can cook up other kinds of restrictions on your coefficients, and maybe you discover another interesting kind of algebra with these objects. I'm just describing to you the state of affairs, but suppose you were the one discovering these things 150 years ago, what you might have been doing. Okay, so by far the most important theorem, I think, for convex sets is if you have a bunch of convex sets, how do you build new convex sets out of old ones? So this is an easily proved result, but a very valuable result, that these convexity is a property that remains preserved under intersection. You may want to draw pictures to see, do you believe that? And because I'm claiming it remains preserved under intersection, do you think it remains preserved under taking unions? If it would, then everything would become too simple, right? Okay. And in fact, it remains preserved under even if you take intersection of infinite number of these sets. Obligatory picture, I put up some convex sets. So the most important convex set is really just the interval. And once you understand convexity on a interval in one dimension, that pretty much suffices to build the theory of convexity in arbitrary dimensions. So that set is convex. That's the awesome. Of course, polygons or half space, intersection of half spaces or other sets. I'm not going to construct these for you, but convexity of all of these types of different shapes, as you can verify, of course, by drawing pictures that, if you make a line between 2 points, it remains in there. Those convexities can be really verified easily by just using that intersection theorem. So here is an exercise for you, that's why. If you haven't done this exercise before, for many of you this may be a trivial exercise, but for those of you who haven't dealt with this concept previously, it's a valuable exercise to try to do. I claim these types of sets are convex, like most importantly half space. So in linear algebra you would start maybe with half plane. Half space is just one side of the half plane. That's a convex set. You put together a bunch of inequalities and equalities. That is a convex set. And I'll prove these two for you right now. If you manage to prove by brute force definition that that's a convex set, this is just an intersection of a bunch of such sets, and hence it's convex. So the intersection rule is your friend here. The other fancy ones one can also verify. Okay. So mostly the kinds of convex sets you can keep at the back of your minds about what we're talking about is just this type of convex set, like linear inequalities. And if you go back into the history of how this stuff was developed, people in linear algebra were going on solving equations. At some points, people said, hey, but what if I didn't have an equation, I had inequalities? What will happen? And it was, in hindsight, this is very simple, but it was when people were studying these inequalities and saying, okay, this can have infinite solutions, what should I do? And it was a brilliant insight of, I think this part is attributed to Danzig, that he said, well, rather than just solve inequalities, I will associate a cost of solving inequalities. So you introduce a cost on, so this is just a convex set, and he introduced a cost on picking out a particular X that lies inside that set. And thus you can say modern optimization was born. And you have more about that later. Okay, challenge number 1. I claim that this set is convex. This is a very famous, maybe less well known, but yet famous in the correct circles, convex set. A and B are symmetric matrices. This is a two-dimensional subset of the plane. It's a non-trivial challenge to try to prove that this is convex. And I'm not going to say too much more about this right now, but just to tell you that this looks harmless, but the convexity of this set is at the heart of at least several thousand papers. Hey, we haven't even worked hard and it already tells me to take a break. Okay. Anyhow, that's the first challenge. Let's now move on from convex sets to objects that we can play with during optimization. Essentially, this is just a related view to convex sets. Once you get the idea of convex sets, then we talk about convex functions. So convex functions will be just functions that have as their domain a convex set and spit out a real valued number. They can even spit out plus infinity sometimes. So I'll call this as the definition. A function is called convex if and only if this epigraph, maybe I'll draw a quick picture for you. So this is f of x. This part above is called the epigraph. If that epigraph is a convex set, then f is a convex function. This is standard definition of a convex function. And another definition is this one, which is called, let's say, Jensen's definition. Function is called convex if its domain is convex, and for any 2 points in its domain, f evaluated at the arithmetic average is less than the arithmetic average of the f at the 2 endpoints. That's one way to read it. Some people read it as f evaluated at a convex combination. I like to call it f evaluated at the arithmetic average. To already spike your fantasy about other ways of constructing convexities, that rather than take arithmetic averages, you may become creative and take other kinds of averages. And that's why I said convexity is very closely related to the study of inequalities. So these functions are called Jensen Convex, named after Jensen. He introduced these formally in a very famous paper in 1905. And in fact, most people only see this as Jensen convex functions. Jensen in his paper also introduced many other kinds of convex functions. Those are built around not taking arithmetic averages, but other averages. But anyhow, this is the definition. And sometimes when faced with a convex function, you could directly try to verify this definition to see if a claimed function is convex. And to remind you, one of the real reasons we are looking at right now is you can keep this statement that I'm going to make is false, but still it's a reasonable working statement, that convex optimization is somewhat easy. So it will help build the building blocks, the toolkit of optimization algorithms. And once we understand how to do convex optimization, we can start using those things or those ideas as subroutines when trying to solve more complicated optimization problems. And soon enough, we'll see another reason. I already drew it in a picture earlier, but another important reason that in the case of convex functions, nature has been gracious to us that we can find the globally best point, global minimum, more easily. I'll quantify for you later when we talk about algorithms what I mean by easy or hard. Okay? You can kind of imagine this roughly in whichever way you wish to imagine, but I'll try to qualify that statement a little bit, what I mean by easy or hard. Okay, so I already answered why we are focusing on these, because they're easy and nice. Here is a picture for those of you who like pictures. Here is another picture. So these pictures are illustrating to, 2 or 3 different ways of viewing convexity. Okay? The first one is saying that F is convex if it lies below the line that joins those endpoints. Right? That's just the definition drawn as a picture. So that's Jensen's inequality as a picture. There is another definition which kind of falls out of the box somehow, but I'm not going to derive it, that if it's a convex function and at a given point you make a tangent, when F is lower bounded by some kind of linear, you can call it affine function. So because this curves like that, at every point you can find a global linear lower bound on the function. That's another pictorial way to describe a convex function. The third pictorial way is this, that a convex function, again this is all, this one is again back to just intervals, but understanding it for intervals really suffices, that for a convex function, the slopes are monotonic. That is, the first derivative increases monotonic. So it shows that's why as you go from here to here, slope of PQ is smaller than slope of PR, which is smaller than slope of QR. So you can see as you move along, the slopes get sharper. And this monotonicity property of the slopes is what characterizes also convex functions. So those were like 3 pictorial ways of characterizing these functions. And why are we doing that? Well, I said that these functions are easy to minimize and they are awesome. But their awesomeness would be kind of lost if we didn't have a good way to check for convexity, to construct convex functions, to detect convex functions if faced with them. Like tomorrow you invent a new cool mathematical model and you say this is cool, but if you cannot come up with even a single instance of that model, tough luck selling it as cool, right? So anytime we construct a distinguished class of functions which we claim that has some interesting properties, we'd better have some way of verifying membership in that class of functions. So these were 3 pictures. You can try to use these pictures for some functions, for instance, x square. I'll just list a bunch of other standard criteria. So each of these things is a claim. And I encourage you to, if you haven't look back at the textbook by Boyd and Vandenberge. They prove all these claims. We don't have, unfortunately, time to prove these claims, so my job is to just expose you to the material or what I think are interesting claims worth knowing, but you should do your share of the hard work if you want to understand this deeply, or maybe slightly less shallow. Okay? Then you may want to verify or prove these claims to yourself. So if it's differentiable, then it is convex if and only if it is lower bounded like that. So that is a very important characterization of convex functions. It is very important, but there are very few times that I have actually managed to use that characterization to prove to myself that the function is convex. Something that turns out easier to use sometimes is that it is convex if and only if its second derivative is non-negative. If it's a vector valued function, then it means that its Hessian matrix of all these second order partial derivatives is positive semi-definite. You can try to verify that. Let's see, I don't remember if I had an exercise for you. Okay, I'll comment about the second derivative part soon. Something that turns out pretty handy is which is why I said it suffices to understand convexity on an interval. Say you have a vector valued function, not vector valued, function whose domain is vectors r to the n. You restrict it to a line by defining just function g of t of single scalar t. So g of t you can show convex along any such direction p. If you can restrict your convex function to a line and show the convexity of that function of a single t, that suffices to establish convexity of the whole function. This is a version that many people use for proving convexity of functions over vectors or more complicated objects. I'll mention this one, and Chapter 3 in Boyd and Vandenberg's book gives you examples and has very nice exercises taking you through verifying convexity of a bunch of functions. There are many other ways. In my lectures slides that are linked from the first page, I have a more elaborate list of how to recognize convex functions. And let me mention here an obvious thing, but nevertheless interesting. When you're given a function f of x, somebody claims to you this is convex. You can try to use these rules to prove it is convex. Something that is easier to do in practice is you start with some simple convex functions and combine them using whatever valid algebraic rules so that you never leave the class of convex functions, you remain convex. That is slightly easier to do. I'll show you an example where just by looking at a function, it's not necessarily easy to verify this is convex. Another very interesting thing, empirically, maybe you could just plug it into MATLAB, Python, whatever Julia, whatever you use. Compute for some random numbers, you know, if f along, just use Jensen's definition. So if on a computer this holds, and if I give you a computer with greater and greater numerical precision, you cannot still conclude a proof. You can increase your confidence if you're making conjectures, but numerically, we cannot even verify a property like continuity. So numerically, verifying something like convexity is completely out of reach. So you can increase your confidence, just like people do, you know, you build automatic differentiation toolkits and sometimes you can there manage to say you manage to differentiate, but even verifying a basic property like continuity is impossible, right, for obvious reasons, because of finite computing time. Okay, so that's why it becomes very important is to start with convex functions and only do operations that preserve convexity. So the easiest one is if f is a convex function, and you just make this, let me call it an affine transformation. Sounds slightly fancier, linear plus some shift. Then you remain convex. So this is pretty cool. You could already see my analogy to linear algebra kind of there, that convexity seems to play sort of okay with a little bit of linear algebra down. So you should verify that. It's easy to verify. But it's the Jensen version of convexity that works easily with this linear algebra. If you had cooked up some other fanciful version of convexity, it wouldn't work out. So this is just to say that, you know, when you define a new class of functions, sometimes good things may hold, sometimes not, depending on what kind of algebra is allowed. Okay. Another one is the standard one which one ends up using, that if you compose convex functions, if you compose two functions, when is the composition convex? And we can have an elaborate set of several such compositional rules. It's very important to know these rules because once you're creating a mathematical model for, say, a machine learning problem or an image processing problem or some other problem in control systems and optimization, then building a mathematical model, if you keep in mind what kind of rules allow you to make a mathematical model which results in a convex cost function, or if you are reading somebody's paper and they make a claim that, hey, this is the convex function, and it's not obvious why it is a convex function, sometimes applying a bunch of these rules may give you guidance on how to rectify it's convex. So this was a toy proof that I included. And once again, Boyden Vandenberg is your friend. Most of the stuff that I'm talking about today has much larger array of worked out examples in that book. And worked out examples really help solidify your understanding. The slides my lecture slides you should just use maybe as a guideline for some of the interesting topics worth picking out as must know. That's about it. So here is my favorite way of constructing convexity. I mean, everybody can have their favorites. Once you know many of those, you may have some of your favorite ways of constructing convexity. This one is by far one of the most awesome ones that I think, that I like, is if you take a pointwise maximum, or rather I should say supremum, fine, you can call maximum, then think of y as a bunch of indexes. So y can be an infinite set, it can be a finite set, it can be a whatever the heck set. Suppose you can index it, that much I ask. And for each particular choice of y, f of x semicolon y. I put a semicolon because x and y are not on the same footing here. So just to remind that. If for any arbitrary choice of y, f of x comma y is convex, then you pick the largest such f out of all possible f of x comma y. That is a convex function. You can do a proof by picture. I, unfortunately, maybe in contradiction to many people, I'm not such a big fan of proof by pictures. Kind of in high dimensions and in other settings, sometimes those pictures can be misleading. This is a fairly easy thing to verify, and you can convince yourself that it's basically because of that maximum in there that stuff will work out. But it's a very important thing to verify. And I'll show you later examples of constructing convex functions according to this definition. Very cool way of making convex functions, new convex functions out of old ones. Something less, so so here I remember this is arbitrary. Something less arbitrary is if you instead of maximizing, if you wanted to minimize. So suppose you have a problem with a gazillion variables, and you want to minimize a function which is function of, let's say, right now 2 variables. Can you eliminate one of those variables? And while we are minimizing. So think of the analogy when we were solving a simultaneous system of equations. One of the first things you probably saw in, I don't know, 8th grade is take the simultaneous system of equations, you start trying to eliminate some variables, reduce the number of free variables, and you then try to solve a simplified system. So the same analogy here, we are trying to solve a minimization problem with a bunch of variables. Can we eliminate the minimization task on some of those variables and then try to solve the remaining for the remaining? And what we want to do is we kind of believe here right now that we can handle minimization of convex functions. So when we eliminate some variables, do we still get back a convex function? And unlike Suprema, where y could be an arbitrary set, when doing minimization to eliminate variables and retain convexity, the original function had better be convex in both its arguments. So this property is, let's say, much more non-trivial. There's a short proof here. I'm not going to go through that. But this property is it's a very important property. But if this joint convexity doesn't hold, then all bets are off. Okay. Now I will start throwing examples of frequently used convex functions that you'll see throughout applications in machine learning. So if you haven't seen these convex functions before, now is a good time to see them. And maybe we'll, as an exercise, anything that I claim to be convex, if you don't immediately see that it's convex, definitely work it out to convince yourself. If you don't work out to convince yourself, you'll forget everything I'm saying here. I guarantee that. It's really crucial to not just believe what I'm claiming here. Same attitude you can apply to any papers that you read. Okay, don't believe what the authors say until you convince yourself mathematically about it. Okay, so for working with objects in vector spaces like R to the n, one of the most important convex functions are what are called norms. Norms are quantities that norms are functions that associate some kind of notion of magnitude to objects in a vector space. And they happen to be convex functions. That's the theorem. So norm is just some function which satisfies this property. It's non-negative. It is zero if and only if its argument is zero. So that property is called positive definiteness. If that positive definiteness property is not fulfilled, that this thing can be zero even if x is not zero, it's called as semi-norm. Positive homogeneity, so if you scale x, remember we are in a vector space, so I can write lambda times x. You can scale vectors. This function scales like that. That property is called positive homogeneity. I mean, like the rest of math, for each concept that you introduce, you invent a name, and sometimes that name is invented to sound more fancy, that we are doing fancy math. Sometimes that name is invented because you wish to refer to that concept so many times, it's just convenient to give it a good name. This is one of those cases where it's good to give a good name. But in many papers, you'll see invention of names to sound more fancy. This property is a really awesome property called subadditivity. This is actually a convexity property because of this bullet point 2. You should verify that. And these three together, functions that satisfy those properties together, we give them a special notation with those double bars. We call these norms. It's just that these functions are so prevalent, we use that shorthand looking notation for them. And that notation is mnemonic. It's supposed to kind of remind you that this is like an absolute value. For a real number, you can take absolute value to talk about its magnitude. For a complex number, you can take absolute value to talk about magnitude. Norms are kind of talking about magnitudes of these vectors. So that's why that mnemonic notation is there. Okay. And the reason I mention this to you, often they come up when solving machine learning problems where instead of just f of theta, you have a regularized model where you add some additional cost function. We'll talk about some of those, like sparsity or L2 penalty, etc. Here are the most important examples for machine learning people. There's a gazillion other examples for everybody else also. But in machine learning, the ones that are most frequently seen, there are some others that I excluded because my slide, I only wanted to have one slide on that. Is this standard Euclidean norm? I'm claiming it's a norm. That means it better have all those three properties, that it is positive definite. So that 0 if and only if x is 0 is pretty clear to see from here. It uses a very basic property of real numbers. To prove that it satisfies that sub-additivity means that you have to basically satisfy triangle inequality. Something you have to verify that. LP norm for p bigger than or equal to 1. When p goes to infinity, it turns into just the maximum absolute value. Frobenius norm is just, treat the matrix as a big box of numbers and take the Euclidean norm. This one you'll see many times. Maybe the most fancy one here is the so-called operator norm. So far it may have looked like it looked exactly like that when I talk about norms, these were trying to measure magnitudes of vectors. But people have extended that idea to measure magnitude of matrices, for instance. And the most common version that you may see is called the operator norm. And that's just basically defined as the L2 norm of like how much can this matrix A expand a given vector. So you take the matrix, hit a vector with that matrix, it reshapes the vector. What is the largest possible L2 norm that reshaped vector can have? Of course, after normalizing, that is called the matrix norm. Some people sometimes confuse that. Hopefully nobody in this room ever has or ever will. This is the largest singular value of a matrix. Sometimes people mistakenly use the largest eigenvalue of a matrix. The largest eigenvalue of a matrix is not a norm, usually, unless the matrix is positive definite, semi-definite. The largest singular value, that gives you the operator norm. Verifying that the above are actually norms as usual. Any of the interesting stuff I'm telling you is an exercise. So I leave all the cool stuff to you. Okay. So far, any questions, or I don't know how you guys are doing it. If anybody wants to interrupt me at some point, feel free to do so. Okay. Or we can even handle that after the lecture, whenever. Just try to, I mean, it may be a little dry because I'm not making any videos or pictures, but hopefully I don't need to entertain you with the television right now. A little bit of algebra is okay here. So my favorite convex function is a much more humble looking convex function, is what is called the indicator function. So this is how we define it. Let's say you have some set x. If the indicator function for that set x is 0 if applied to a point lying inside that set, plus infinity otherwise. And this indicator function is convex if and only if the underlying set is convex. We call it extended value convex because, unlike some of the examples I showed previously, this function is allowed to take on the value plus infinity. And it's a really cool thing. Convexity is a study of inequalities, as I said. And then you have to start becoming a little careful when your inequalities may include plus infinity floating around somewhere. Well, as long as you don't subtract or multiply with negative numbers, mostly inequalities involving plus infinity will remain well behaved, right? You can find that. So this indicator function is a really cool function. It allows us, at least abstractly, to turn problems that have constraints. You want to minimize a cost f over x satisfying some constraints, that is, minimize the cost subject to x lying in some convex set. You can turn that into an unconstrained problem using indicator functions. I'll show you. So I don't want to interrupt it right here. I'll show you later exactly how. Okay, and I'm showing this function here because it is very useful when describing the next class of super important convex functions, which is related now, related to the norm stuff that we talked about. So the most important, one of the most important ideas, or let's say one of the most important applications of suprema over arbitrary index sets spit out convex functions this is an application of that general lemma. So remember I said, if you say f of x is the supremum over f of x semicolon y, where y is any kind of index set, you take that supremum, you get out a convex function. So if the function over which, if that f of x semicolon y looks like this right hand side, well, I'm calling it z here now instead of y. Sorry, yeah, it's f star of z, and instead of y, I'm calling it f. This is how we define Fenchel conjugate. And you may wonder, where the heck is this coming from? Actually, Werner Fenchel created this in a very famous landmark paper, I think it was 1954, but my history is not so powerful. Wikipedia's is better, so you can check there. So one of the reasons there are several reasons for considering such a function. One of the main reasons is it proves very handy when trying to do optimization with constraints. So let me just abstractly leave it at that. And partial insight for that may come from, I said, if you have a convex function, you can construct these global linear underestimators, right? You can, global linear underestimator is a big sounding word for, I have this curve, I can put several lines down there. And you can make many of those. One of those ends up being kind of the tightest. Out of all the underestimators, this one is the closest to the function. And that one is, of course, the underestimator given by tangent line. But one way of thinking of that tightest underestimator is really looking at the best global linear underestimator there. So you get that function out. I just wrote it as supremum. You can write, minus of inf of minus. So an often used trick, really fancy trick. You have some functions, you want to compute its supremum, you often do minus of infimum of minus of h, or vice versa. So you can write that as a minimization problem. Break number 2. That is great. I forgot to switch off my screen. Okay. By the way, using this very deep theorem, supremum is, you can do sign flips. Maybe I can raise it here. I mean, you can just flip signs and write supremums as infimum. You see that if f of x is a convex function, this is actually a convex optimization problem. So another mnemonic, keep this in your minds. If you haven't done this before, it's good to establish muscle memory of convexity. Whenever you think convex, always think in terms of minimization. Minimization of convex functions is the numerically tractable thing to do. Maximization of convex functions is not tractable, typically. And to express this mnemonic in a further way, whenever we write inequalities involving convex functions, you can set this in your mind. You can, of course, pick the directionality of inequality which agrees with your personality, whether you like maximization or minimization. But it's usually safer to make a choice and stick with that so that you don't misconclude convexity of something. So usually for convex functions, it's cleanest to think in terms of minimization because that's the tractable thing. And inequalities involving convex functions typically are most safely written as f of x less than equal to something. If this direction flips, then you lose convexity. For the simple reason Jensen's convexity is defined as f of blah is less than equal. So, however, if you recall, I said the suprema over that arbitrary function family is going to be convex as long as for each z it's a convex function. So here, if f of x is any function, even if it is not convex, what you get out is convex by using that suprema law. Because the inner side is a linear function of z, linear functions are convex, and you supremize over infinite number of linear functions, you get out a convex function. Very important property. So actually I feel bad, I forgot to, I did mention it, but I forgot to stress it that by far the most important class of convex functions are linear functions in vector space. And if we didn't include linear functions in our class of convex functions, then we wouldn't be able to construct any of the theory of convex optimization. So they are really basic. Okay, that was just some technical remark here. Here is a cool example which now uses all the concepts that I have talked about so far. F is a norm, and I'm trying to construct the Fenchel conjugate, this conjugate function, and that conjugate function can be written as a certain indicator function. So this puts together all those three concepts in one exercise. And the mnemonic to think about here is that if you have a norm, the Fenchel conjugate of a norm is the indicator function of its dual norm. So far, unfortunately, only jargon. Here's a proof also. I'm not going to go through that. But this is a very important proof, very important, I call it example. It's a, let's say, a building block result. Because when designing optimization algorithms, if you're using a norm as a regularizer, I'll show you in the next lecture actually this particular example in action. Sometimes it helps to reformulate the problem in terms of the dual. So that's why understanding how to make these Fenchel duals, I'm calling it Fenchel conjugate, it's also called Fenchel dual, how to form these for given functions is a very useful skill to acquire. May help you simplify a problem that you're faced with. So, and by simplify, I mean that it may become numerically easier to solve or conceptually easier to solve. Yeah, it is exactly like that. Here, let's just think these are vectors. So it's really the standard way to do the dual norm. For matrices, you can think in terms of dual norm in the operator space. Yeah. So in some sense, you can think of, yeah. Well, okay, let me not go in there. Nothing helps like simpler examples. So here's a good exercise for you. If you have a quadratic function, let's do this exercise as I walk through this. So this is a quadratic function. A is a positive definite matrix. I hope everybody knows what a positive definite matrix is. And to be pedantic, I can say, let's say it's a symmetric, real symmetric positive definite matrix. Some people in math use positive definite even for non-symmetric matrices, but for us, when I say positive definite, I mean real symmetric. I mean, we are not going to work with Hermitian matrices, but anyhow. So if you take the second derivative of x transpose AX, what's the second derivative? It's just the matrix A. And hence, from that previous theorem long ago, second derivative being positive definiteness is sufficient for convexity. So this function is convex. It takes some exercise to find out what the Fenchel conjugate is. Unfortunately, there was no perfect way to order these. To obtain F star, you have to actually solve an optimization problem. And I've not yet talked about solving optimization problems. I'm just describing notation so far. But fine. This is called the hinge loss, which comes up in support vector machines. You may have seen that. And this is another notation that you may read in papers, that if you take the conjugate of the conjugate, you get back the original function. Then you say the function is a closed convex function. Doesn't happen for all convex functions. But for most convex functions that we are ever going to deal with, f star star is f. As an analogy now, back to linear algebra land, if you take the orthogonal complement of the orthogonal complement, you get back the original space. Or in matrix lingo, if you have A transpose and you transpose it again, you get back A. So this operation in algebra is called an involution. So you do this for convex functions, you get back that f. But if you try to apply this operation to see the coolness of that operation, try to apply this biconjugation operation to a function that is not convex. Because remember, I just now said, when creating a Fenchel conjugate, f does not need to be convex. You can create a Fenchel conjugate for any function. The Fenchel conjugate itself will be convex because it's just a pointwise suprema over blah, over convex functions. But f need not be convex. Which means if you do f star star, I don't think you're going to get back f, right? Because f star is convex, the star operation retains convexity, so f star star is better spit out a convex function. But f is not convex to begin with, so tautologically you can see it's not going to be something what you expect. But it's worth working out to see what comes out. Then you can make a theorem like, the nearest convex function to this quasi-norm, blah, 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 but then you'll see it's actually much less dramatic than what I said. This is also a good exercise. This one is an exercise in linear algebra to see what may the conjugate be. Okay. Here is challenge number 2 for those who like playing with toy math problems. Here's a very cool challenge. This is one of my favorite questions. Trying to prove convexity. This is just for your entertainment, okay? Nothing. It is a problem which actually comes from probability theory, from the so-called coupon collector problem. But anyhow, that's just an aside. So I have this alternating, 1 by x for one variable. If I have two variables, so you have sums of inverses minus this taken in pairs plus taken as triples, and you can generalize this. First exercise to prove that this function is positive. It's easy, but it's not trivial. It's a good exercise to try out. Hard exercise is to prove that these functions are actually convex in all the variables, okay? X, Y, Z, all the variables taken together. The variables are strictly positive, okay? That's important. I don't want to do 1 by 0. And in fact, one can prove something even stronger, which is even harder to prove, that 1 divided by h is concave. But for those who want a challenge, try proving that this is a convex function. Feel free to use any of the recognizing convex function lemmas I stated, or any other lemma that you can find anywhere else. It's a very interesting, but it's not an impossible thing, but it's a very awesome kind of thing to see that, okay, something that looks pretty, has so much symmetry, and we know so many ways of recognizing convex functions, it's not always so easy to recognize convexity. Anyhow, that was an aside. Finally, after having established that vocabulary, and I should squeeze in a little bit information about now using that vocabulary to do what we are actually interested in, is to solve optimization problems. Okay? So, generically, so let me give you an outline of what I'm going to talk with you about in optimization. So my focus throughout here right now is convex optimization as a building block for more complicated optimization. And the kind of optimization methods and techniques that are popular in machine learning are actually very simple optimization methods. Some of them are so simple that there was a time when people used to condescend upon them because they were so simple. It's unfortunate human nature. But all of those have one thing in common, that they're all based on gradients or subgradients. So they are so-called first order. First order, the word first order comes from you take f of x and you take its first order Taylor approximation. First order approximations of functions are defined by, and they in turn define the concept of gradients or derivatives. And that's the level of complexity we are going to touch in this course. That suffices to run TensorFlow also, to care about that. So that's why I'm gonna just focus on that, and I will introduce to you some simple ways to use this first order conditions for talking about optimization. That's one of the classical uses of calculus that you have also seen in high schools. And for convex functions, that first order idea of first order, like of gradients, can be remarkably extended to even non-differentiable functions. And in convex optimization, we love non-differentiable functions because they include things like constraints. You saw that indicator function. Sometimes it's 0, sometimes it's unhappy and becomes plus infinity. It's not a differentiable object. But we want to deal with such objects because we want to deal with constraints in optimization. Hence, extending the theory of gradients to non-differentiable objects is a very important piece, centerpiece in the world of convex optimization. Of course, the engineering motto here is, differentiate it willy-nilly. Will still work out. But if you don't know what's happening behind the scenes, if it fails sometimes, then you won't understand what happened. The mathematician's motto, it's a non-differentiable over set of measure 0, hence it doesn't touch me. I don't care. But that's really the opposite of what we want here. That non-differentiable set is the one we care about. Okay, so let's talk about optimization. Now let me expand that f of theta thing that I said to something more fancy. So this is called a standard nonlinear program. You have some cost function, you have a bunch of constraints, and of course, for that problem to be reasonable, x had better lie in the domain of all those guys. So I'll just drop those conditions of the intersection of their domains being non-empty. It's tautologically true, but if you're formulating a problem, you may or may not a priori know that your functions have empty domain or not. If I give you a bunch of functions and I ask you, is their domain intersection empty or not? That's another optimization problem. We just assume that happens, that you did the modeling job correctly. So think of it always this way. When we are doing optimization, it's not that somebody is really coming to you that here is an optimization problem. You may be the one formulating your application as an optimization problem. So these things are often under your control. And part of the art of doing optimization lies in being able to take problems and turn them into this form. We don't have that type of time in this lectures to go through the mathematical modeling part, and just establishing the alphabet with which you can subsequently write sentences in this language. Okay, so again, some jargon as usual. If all the Fi are differentiable, we call it smooth optimization. Distinction from mathematics. In mathematics, when people use the word smooth, they mean C infinity, infinitely differentiable. In optimization and machine learning, when we say smooth, we mean once differentiable. We are less demanding. If any Fi is non-differentiable, we call it non-smooth. If all the Fi's are convex, we are in the happy land of convex optimization. And if there are no constraints, then lo and behold, it's called unconstrained optimization. Okay. So that's the lingo. Some other lingo. So if X is the feasible set, so there it would be, you know, all the X's that satisfy this, that's the feasible set. The optimal value, this notation is common to what you'll find in Boyd's book, so I'm using that notation. So once you look back at that book, you'll make a connection. So the optimal value of your optimization problem, we'll call it P star. P star is a mnemonic for the primal optimal value. So if the feasible set is empty, we say the problem is infeasible. And if the problem is infeasible, infima is defined to be plus infinity. That convention works out well. One can prove that that's the only convention that will work out well, but just believe me for now. If you can minimize it all the way down to minus infinity, then of course it's unbounded. For instance, try to minimize x. X is a linear function, it's convex, right? Minimize it on R, where does it go? Minus infinity, so it has an infimum but no minimum. Something that looks less trivial like minus log of x. Minus log of x is a convex function. Take the second derivative in your head and convince yourself immediately. And so basically sometimes minimum doesn't exist. And if there is no cost function, just constraints, it's called a convex feasibility problem. All these constellations occur. And we will take for granted that you manage to formulate a problem for which there does exist a minimum. Okay? And it's not always a priori clear that problem has a minimum. People dedicate some study to that. And this is one other fancy, nice place where convexity may help. There are non-convex problems where verifying whether the problem gets unbounded below or not can be NP hard. So even these mundane things can fail. So it's good to know that, you know, these objects typically all will be well. You have a problem, it does have non-empty feasible set, and you can actually construct minimum, etc. But it's not always granted. Okay. So a point is called locally optimal if around it there is no other point with smaller objective function value. If over the entire set there is no other point with smaller objective value, it's called globally optimal. Of course, you can have more than one point which has the same globally optimal value, right? Here is a convex function. This entire interval of infinite number of points have the same globally optimal value. And if the function is curved, so this one is non-differentiable at this kink and this kink. If it is differentiable, then it only gonna have one optimal point. And the most important property of convexity that I've already mentioned for optimization is local optimality implies global optimality for convex minimization. And that's the reason why we got lucky. So as Nestrov says in his book, that, you know, typically all optimization problems are unsolvable. What he means is that solving optimization problems to global optimality cannot be done in general. In the case of convex optimization problems, we are lucky. Nature granted us that local equal to global. So I'll expand a little bit on what I mean local equal to global. And this is one way. Suppose function is differentiable. You know from high school calculus generalized to vectors now that first derivative equal to 0. Here the gradient is vector equal to 0 is necessary condition for optimality for any function, convex or non-convex. This is necessary. But the beauty of convex optimization is this simple first order condition is also sufficient. And that's where all the difference comes from. So in general non-convex optimization, this is just a necessary condition For convex optimization, this is also a sufficient condition. You can verify that property. It follows purely by definition of convex functions. But nevertheless, those of you who don't see this right away, please use one of the three definitions of convex functions I showed you, and you will see exactly the beauty of this property. Okay. Now, I have 15 more minutes, so I'll introduce to you constraint optimization. I wanted to also introduce to you more fancy stuff like taking duals, etc., but I think I was too ambitious about that. So let me just talk to you about constraint optimization. And in the afternoon lecture, I will talk about duality and actually using all this stuff in concrete examples where we just use it. So I'll introduce it along the way. So this is the definition of convexity. If you have constraints, then the gradient disappearing. So if you're trying to minimize f of x such that x lies in a constraint set, now that you have constraints, the gradient equal to 0 is no longer the condition that determines optimality. Because you also have to satisfy constraints. The gradient may be 0 at an x that lies outside the constraint set, hence. So the condition you get is this. I actually even have a picture. It has an x instead of y. So this basically says that, you know, a point x star is going to be optimal if for any y inside the feasible set, that's the angle your gradient makes along this line. And these dotted lines, the more inside you come, the smaller the objective function value. Yeah, if I had time, I would actually show you. There are like 3 ways to prove that I know of. I would have liked to show you one of my favorite ways of doing proofs, which is just proof by notation. You define enough notation and then you say, in this notation, this is true. So those proofs are good because that means the notation was very effective. So let me just now talk a little bit further about this very important concept that I mentioned, that we are now looking at first order conditions. First order because it's the first derivative. First derivative equal to 0 or this inner product being positive for all feasible y. These first derivative 0 unconstrained conditions, if and only if necessary and sufficient for convex problems. This condition is necessary and sufficient for constrained convex problems. You will almost never find anybody using that particular condition ever. Because your constraint set X, if it's given by, 50 or 100 or 1000, whatever different little FIs defining the constraint, good luck verifying that condition. And huge amount of effort in the world of optimization was then invested by people to try to come up with different instantiations of this optimality condition. So the gradient based condition is kind of easy. You have f, you can write down a derivative if you can, okay. So if you can write down a derivative, you can kind of get a feel for that I've got to solve these nonlinear equations and I'll get an optimum, fine. We don't solve it that way because solving nonlinear equations is really tricky. For constraint problems, we have this tautological kind of definition, but verifying this is really hard. And my last slides, which are really far down the road, construct for you that if you simplify this condition, combine it with definition of duals and simplify that condition, you end up recovering what are known as the KKT optimality conditions. If you've heard of KKT, Karosh-Kuhn-Tucker conditions, you'll see that in chapter 5 in Boyd's book. I'm not going to have the time to derive that, but just saying to give you intuition that those so-called KKT conditions are an instance of that. Same thing. And this itself is an instance of, this condition itself is just an instance of the gradient disappearing, but now not the gradient disappearing because we have a constraint problem, it's a subgradient, roughly speaking. So let me show you that. So really that's what I mean, that there's a very simple proof by, like you generalize high school calculus of derivatives to subderivatives, that is gradients to subgradients. Gradient equal to 0 was good enough for unconstrained, and a subgradient being 0 will be good enough for constrained optimization. And a subgradient being 0 yields this type of stuff and all that KKT business as just byproduct of pure definition. So let's just look at subgradients before we wrap up for the morning session. So optimization via subgradients. Here is this definition. I didn't draw by at the correct place, but you can now, I already gave you the proof of your homework exercise, that if you draw these tangent lines, we had this definition that f of x is bigger than f of y plus this derivative, right? This is the first order Taylor approximation, throw away the rest of the stuff. So from this definition you can see, if the gradient at y goes away, what happens to y? By definition, it's the minimum or a minimum. So nice things about that definition, right? So when the function is non-differentiable, it has these corners. So the parts where there are corners, you won't have a single unique supporting hyperplane. You'll have an entire family of these hyperplanes, which give you a bunch of linear functions. So you can draw that picture and see how many different linear functions you can make, that remain below your convex function. So you no longer have a unique linear function, tightest linear function as you had here, but you have many of those. And each of those can be, defining vectors that defines that hyperplane can be called a gradient-like object, and that's why we call it subgradient. And you can see again, as you rotate those subgradients, if one of these, if you at a given point you manage to find some g vector which is 0, that point has to be minimum again. So that's basically it. You manage to extend the notion of gradients to subgradients. And the reason all of this works out so coolly is because for us, as we are studying convexity, it's these inequalities rather than equalities that are more important. And you can satisfy this inequality with vastly more number of vectors than you could satisfy equality. That's why roughly we managed to take the concept of gradient to subgradient. Okay. Some simple facts about subgradients. Bottom line message, subgradients are easy. You can easily construct subgradients. So something that had better be true, if f is differentiable, then the gradient had better be the only subgradient. A cool property is that actually if you manage to show for a function that it has only one subgradient, then this function must be differentiable, and this one thing that you found must be the gradient. So converse to line 1 also holds. That's a beautiful property also, though it's kind of roundabout way of going and proving that a function is differentiable. Fine. And the nice thing, as far as building algorithms is concerned, computing one subgradient is typically not more expensive than computing f of x once. Big O of that. So wherever we use gradients, if we could use subgradients, life's good. And the hard thing is determining all possible subgradients at a given point. That is really hard. So in that picture I drew, it was easy to make those planes, but high dimensional convex function with bunch of constraints, understanding all possible vectors that lower bound your function, really hard, extremely hard. And what do we do with such extremely hard problems? Typically we ignore them. Not always, but typically we ignore them, okay? And, okay. And very cool fact that just like you have differential calculus, which was invented back in the day, really far back, with bunch of rules. You know, you take sums of functions, you can differentiate that sum of the, and you can take compositions and scale them or multiply them, and you have different rules, chain rule, product rule, etc. That calculus exists for differentiable functions and hence for multivariate functions. A similar but more refined and careful calculus also exists for non-differentiable convex functions. Convexity is crucial here, very crucial. And one of the shining achievements of the field of convex analysis, the reason because of which the field gets to be called analysis, is the construction of a calculus of subgradients. Most of it was done by Rockefeller during his PhD thesis. So this is the kind of stuff that you should look for in PhD work. Okay, so I think I'm going to have to wrap up soon, but I wanted to mention to you one example to show you that computing subgradients is easy. Look at that. F of x is supremum. It's one of our friends, you know, supremum over arbitrary family. And you want to compute some subgradient. The set of all subgradients is denoted by that partial of f. You want to just compute some vector. So, simple way to do that, pick a y star for which this thing is maximized. And then h of x comma y, h is a convex function in x for every y. Just pick a subgradient of that. And one has to, of course, prove that. There's a bunch of other such rules of constructing subgradients. The important thing why I'm mentioning this to you is we'll soon look at in the next lecture bunch of optimization problems where you can just directly, rather than taking gradients, take subgradients and then plug it into an optimization subroutine which uses subgradients to optimize that cost function. So once you understand how to compute subgradients, maybe somebody also built an auto differentiator for subgradients, you can plug it in and use it. And most of the time, let's say the moral of the story is, if you do the obvious thing, that is usually a correct subgradient. Of course, obvious after you've seen all the multiple theorems of how to construct them. So look at my lecture notes, or Stephen Boyd has a very nice, even more expanded, not slides, a typeset set of lecture notes on how to construct subgradients. You may benefit from that. And this object is a starred section, which is starred for very obvious reasons, and that reason is that I'm not going to cover it, but I put that section in here for your reference. This section summarizes this grand achievement of calculus that I mentioned, that you can do calculus with non-differentiable functions. But it's important, if these functions are non-convex, then that calculus doesn't exist. Only parts of that calculus exist. So its convexity is really crucial for many such things. The subdifferential is a very cool object, but it's a starred section, and I'm going to skip that. And I think I'll come back to the other parts. I'll stop. Okay, maybe I think I'll just stop. But like this, I'll stop at where I'm going to start next time. Like this cool calculus rule. So I'm not. I hadn't planned to talk about that. But just this final thing. Gradient equal to 0, proof by notation of all KKT conditions, everything just is a byproduct of this. The following definition which I attribute to P. F. Emma, because even though he didn't have subdifferentials back in 1600s, it's essentially called his rule. So if f is some convex function, let's say convex, then the set of minima of f is the set of all the vectors in X where 0 lies in the subdifferential. So this is not a gradient. Subdifferential is a set of potential vectors. Gradient had to be, if this set is a singleton for differentiable functions, so for differentiable functions this will become 0 equal to, otherwise it's just 0 belongs to. And the set of minima of f coincides with the set of vectors where 0 lies in corresponding subdifferential. And using that, it's a one-line proof of Fermat's rule, so by definition. And that's why I said if you start trying to minimize f of x with constraints, write f of x with the indicator function. These two problems are equivalent. So that's just the exact same problem. And now it looks like a non-differentiable problem in line 2 here. To this you apply Fermat's law and simplify whatever you can based on what you know about x. You recover different types of optimality conditions, including that optimality condition even for differentiable problems, pancake it and whatnot. So it's really just coming from this very simple thing. That's the power of good notation. And I think I will stop with that, and yeah, any questions, I can answer them now or whenever.
Is there anything that you can say about constrained optimization problems where the domain is not convex?
Yes, I can say something there. So first, I hope everybody got the question. So the question is, what can we say about constrained optimization problems where the domain is not convex? So let me slightly refine that question. If we are working with convex functions, the domain had better be a convex set for us to call them convex functions. So that means we are working with some function which is not convex. So one of your constraints, let's say, is non-convex. What do you do? So you can still optimize them using gradient-based optimization, but it's not easy to do subgradients there. There exists a notion of subgradients also for non-convex functions, but it's not so easy to do that. I will show you later a few techniques of dealing with non-convex constraints. I will show those techniques tomorrow. That I have a cost and I have non-convex constraints. We have to be slightly more creative in what we do. And in the end, we still use, so if your constraints are defined by a cost function that is differentiable but non-convex, things are still easy. But if your constraints are defined by a non-convex function which is non-differentiable and non-convex, then typically all bets are off. But we can still try to approximately do something. So I'll give some examples tomorrow of general techniques for this case. Any other question? Then have coffee to generate questions and rather answers to my challenges. Those are what I'm more interested in.